All right, so 19. We're going to look at tests for symmetry and even and odd functions. And this may be something you touched on a little bit in Algebra 2. I don't think that if you did, I don't think you spent a whole lot of time on it. But the symmetry aspect of this, you've been talking about symmetry like forever. And algebraically, you've been looking at symmetry since it was in 8th grade math, it was in geometry, and then a little bit in Algebra 2 for sure, at least a little bit. So for these first two graphs here, it says the graph can be reflected across a line so that the graph coincides with itself. Now, when you first learned symmetry like this back in elementary school or whatever, they may have talked about it more as folding, like you can fold something on top of it, onto itself, like a butterfly or whatever. But it's not really a folding. Yes, I could fold this on the x-axis and it folds onto itself, but that's not what's happening. It's being reflected across the line. So if I take this graph right here and I pick it up and I reflect it or flip it around the x-axis and set it back down, it'll look exactly the same. So you need to think of it more as a reflection than as a folding thing. But if it has symmetry like this, this is called line symmetry. That is definitely not a new thing. Then we also have a type of rotational symmetry over here. So if the graph looks unchanged when rotated 180 degrees about the origin, so this would be the point of rotation, and if you rotated 180 degrees, rotational symmetry was probably a new thing to you in geometry, but definitely part of geometry at any level. So if I rotated 180 degrees, it should look the same. So if you take the paper and you rotate it 180 degrees or flip it upside down and the graph looks exactly the same, then it's got point symmetry. All right, so those two things should be old business for sure. So then we say that the x-axis and y-axis are common lines of symmetry. They're really the only lines of symmetry we care about graphically. Okay, yes, something can have different lines of symmetry, but these are the only two we focus on. And then the origin is a common point of symmetry. So again, we could have rotational symmetry in some of these graphs, but only if it's origin symmetry do we even care about it. Okay. So let's look at graphical tests and algebraic tests. So yes, you can just kind of look at a graph sometimes, but we got to look at the graphical part of it algebraically as well. So the following graphical algebraic tests can be used to determine if the graph of a relation is symmetric to the x-axis, y-axis, and or origin. So if we want to think about it x-axis wise. Now again, as far as these ordered pairs are concerned and what sign changes, all that starts in 8th grade math. You look at reflections algebraically there. So if you get them mixed up, it is so easy just to take a point and think about what's happening. If I have a point right here, and I'm going to reflect it in the x-axis, it ends up down here, right? Did my x value change? No, the x value stayed exactly the same. So if I have x-axis symmetry for every point xy on the graph, the x value is exactly the same. The y value changed, but what's the only thing that changed about it? The sign. Okay, so this is negative y. And that way, if you get confused on which one's changing, just take one point and think about literally what is happening. So on a graph, for every point xy, there is an x negative y that's also on the graph. Algebraically, if I just have the function and I'm trying to figure it out, what we're going to do is we're going to replace y with negative y, simplify things out, and then if I get the same, it looks the same as it did in the beginning, then I have x-axis symmetry. If it doesn't, it look the same, then it doesn't have it. Okay? So then y-axis. Well, if I take this same point and I reflect it in the y-axis, it ends up over here, right? So now the y value didn't change, but the sign on the x did. Okay? So y-axis symmetry, you change the sign on x. X-axis, you change the sign on y. So algebraically, we replace x with negative x, and it results in equivalent equations. Then origin symmetry, and this is a rotational symmetry. Well, when you reflect in intersecting lines, that's also the same as doing a rotation. So if I think about this point and I reflect it in the y-axis, then I reflect it in the x-axis, it's the same as rotating it. Now, this is 90-degree angle because these are the axes, right? And so that means that this is actually a rotation of 180 degrees. And remember, you always rotate counterclockwise unless you're told otherwise. So from here to here would be my 180 degree rotation. Well, to get from here to here, if I reflect here, I change the sign in x. Reflect here, I change the sign in y. So for every point x, y on the graph, there's a negative x, negative y. That's also on the graph. So algebraically, when I test this, I have to replace x with negative x and y with negative y and see if it results in equivalent equations. Okay? What questions do you have at this point? All good? All right, so it says, use the graph to determine if the relation is symmetrical to the x-axis, y-axis, and or the origin, and then confirm your answer algebraically. Okay? Now, I'm only going to make you confirm the one you think it is, meaning that you're not going to have to confirm all three of them, like confirm that it doesn't work. So when you look at number 1, from the graph, this has what kind of symmetry? X-axis, y-axis, or origin symmetry? Y-axis. Okay, so we're going to say we think it's y-axis, right? So then we have to confirm that algebraically. In order to do that, so when you confirm y-axis symmetry, you replace x with negative x. So I've got y equals negative x to the 4th minus 4 times negative x squared. And let me remind you that negative x to the 4th does not equal negative x to the 4th, right? Those are two different things right there. Because this right here means you take it to the 4th, and then whatever you get, you make it negative. Here, that negative is also taken to the 4th. Okay, make sense? So when you're substituting it in, make sure you're writing it correctly and you're thinking about what's happening in there. So when you take negative x to the 4th power, what do you get? Positive x to the 4th power, right? Minus 4 times, well, negative x squared is just x squared. So this is identical to this. So there's the confirming it algebraically. You have to show that you substituted in, and then you have to show the last step. If there's other steps in between, whatever. Sometimes there may be. But those two things have to be there because you're proving it. You can't just look at it and say, oh, well, I know that's going to happen. That's great. That's not you showing algebraically that it's happening. Okay? We good? All right, so what kind of symmetry does it look like number 2 has? Origin. Okay, so it's not x-axis or y-axis, but we will go with origin. I agree with that. So to test origin, you have to substitute in negative x and negative y. So I'm going to do negative x times negative y equals 6. Well, what's negative x times negative y? xy, positive, good, equals 6. And we have confirmed it. Okay, we good? Any questions? Awesome. Alrighty, number 3. X-axis, y-axis, or origin, or none, or all, or x for sure. Okay, is that it? Okay, if I was to just draw this over here, and let's pretend like it's actually perfect. Does this have 2 lines of symmetry? Yes. Does it have point symmetry also? Yes. But this isn't just asking you about line symmetry and point symmetry. They specifically have to be these 3 things. If I rotate this 180 degrees about the origin, it's going to be over here, right? And if I reflect in the y-axis, then it's going to be over here as well. Okay, so that's why this one only has x-axis. It's all about, where it is too. So to test x-axis, we substitute in what? Negative y. So I'm going to get 4 times x plus 3 squared plus negative y squared equals 16. Well, there's absolutely no need to square this out because I want it to look like that in the end, so I just rewrite that. 4 times x plus 3 squared plus y squared equals 16, and I get equivalent equations. Okay. Everybody good? All right, so what do we think about number 4? X-axis? Yes? Y-axis? Yes. Origin? Yes. So it's got all 3 of them, right? So that means I have to show algebraically all three of them, and I'm going to label what I'm doing here. So for x, I'm going to replace the y. So I get negative y squared minus x squared equals 1. That means I get y squared minus x squared equals 1. Well, that's what I was hoping for. Then for y-axis symmetry, I'm going to do, I cannot write that. I'm going to do y squared minus negative x squared equals 1. So that gives me y squared minus x squared equals 1. And then for origin, negative y squared minus negative x squared equals 1. So y squared minus x squared equals 1. All right, what questions do you have? Good? All right, look at number 5. Do we have x-axis symmetry? No. Y-axis? No. Origin? No. Almost, but we're off a little bit, right? Like it does have rotational symmetry, but it's not on the origin, so it's none. And then you don't have to check anything, okay? But let's say that on here you only put x-axis and that's checked, then you're not going to be right. I mean, I'm only making you check what you have to check, but at the same time, you still have to have everything there that's needed. All right, what about number 6? What kind of symmetry? Y-axis, all right? So we're going to do y equals negative absolute value of negative x minus 2. So what's the absolute value of negative x? X. So this is y is equal to negative absolute value of x minus 2. Basically, you're taking out that negative 1. The x still has to stay in there. And then it looks the same, so we're good. All right, what questions do you have? All righty. So now we're going to look at even and odd, which is really where we're really going with this because it's all about functions, and we focus way more on functions. Up here, of these 4, which one of these 4 are not functions? 3 and 4, right? So those 2, neither one of them are functions. We agree with that? What kind of symmetry do they have in common? X-axis symmetry. So if a relation has x-axis symmetry, it can't be a function, because just by the nature of what that is. So when we're looking, that's why there's just 2, even and odd, even though we had 3 types of symmetry here. X-axis doesn't work with functions. So even and odd just uses y-axis and origin. So a function is even if it is symmetric with respect to the y-axis. Okay. So the good thing is for when you're testing even and odd, instead of worrying about substituting a negative x or a negative y, since these are functions and technically there's not really a y there, instead we're just substituting in a negative x every time. So if I find f of negative x and it equals f of x, so basically I substitute in a negative x and I get the same thing back, that makes it y-axis symmetry, right? So if f of negative x equals f of x, then I'm good, okay? And it's y-axis symmetry, which makes it even. Then a function is odd if it is symmetric with respect to the origin. The algebraic check here is f of negative x equals negative f of x. You get the opposite of f of x, basically. Now, we've got to make sure we read the directions and we actually answer these questions fully, because it says determine algebraically, which means I got to show some work, if the function is even, odd, or neither, and if it's even or odd, describe the symmetry. So yes, that is part of the answer. So in order to figure out if it's even or odd, you start by finding f of negative x. So here that is equal to negative x cubed minus a negative x, right? So what's negative x cubed? Negative x cubed, right? So this gives me negative x cubed plus x. We agree with that? So now this does not look exactly like this. So it does not give me f of x. If I factor out a -1, then I get x cubed minus x, right? And is this the same as this? Just what's inside the parentheses? And that is f of x. That means then that this is equal to negative f of x. Make sense? I just substituted this part right here for f of x. So now, since f of negative x equals negative f of x, is it even, odd, or neither? Odd. So this is an odd function, and then we have to describe the symmetry. Since it is odd, it is symmetric, and we can abbreviate symmetric with SYMM. Symmetric with respect to the origin. And make sure in your statement that you have started by actually writing that part down, like literally f of negative x, and then at the end, whatever it happens to be, whether it's f of x or negative f of x, that you actually have the beginning and the end there. That's what's justifying that it's odd. Okay? Then it won't be a function, and so it won't be one that's given to you right now. Because these are functions, so that's a good question. All right, so let's look at number 8. I'm going to find f of negative x. That's equal to negative x squared plus 6. Right? So negative x squared is just x squared, right? And we make it negative, so that's equal to negative x squared plus 6. Does that look exactly like what we started with? Yes, so then I say that equals f of x. So I've started with this, I've ended with that. So is it even, odd, or neither? Even. So then I say it's even, and it is symmetric with respect to the y-axis. Okay. All right, let's do number 9 together. I'm going to find f of negative x. Oops. That's equal to negative x cubed minus negative x squared minus 2 times negative x. So this gives me negative x cubed minus x squared plus 2x. So does that look identical to what I started with? No. If I factor out a -1, will it look the same? So if I say this is equal to negative, then x cubed plus x squared minus 2x. Does it? No, it doesn't. Okay, so sometimes you got to do that and then like, oh, that doesn't match either. If neither one of those matches, then it's neither. It's still a function, but not every function is either even or odd, right? That's just a classification that we have. It doesn't have to be one of the two. Okay, we good? All right, y'all do number 10. Go ahead and go on to the next one. Good. All right, go ahead and move on to the next one. Good. Okay, how'd that become negative there? If you square it, it's going to be positive. Good. Okay, good. And don't forget, you have to put symmetric with respect to. Okay, keep going. No, you're fine. You're fine. Did I check out? Are we good? Yes, yes. You're missing a whole lot of stuff. That should say f of negative x right there, right? and then it equals f of x, and then you have this, and then you have to, you didn't do that on any of these. Have you been paying attention to me? No, you didn't. No, you didn't. You check your numbers 7 and 8. You tell me, the last part of the question. Oh, yeah. Yep. And you have to have the beginning and the end, Michael. You have to have this equals this. Then you say if it's even, odd, or neither. Then you got to have symmetric with respect to y-axis. Come on now. All right, so I think most of y'all have gotten through 11, so I'll go ahead and we'll work it together, see if we agree. So f of negative x is going to be negative 8 over negative x, and then the negatives reduce out, right? So I get 8 over x. It does not match the original, but if I factor out a negative 1, will it? You don't think so? So if I factor out a negative 1, then it's going to give me negative 8 over x, right? Because negative 1 times that, right? Because you don't multiply to the numerator and denominator, just one of them. So this does equal negative f of x. Come on now, fractions. Whew. Fractions, you gotta love them. Okay? So that makes this odd, and it's symmetric with respect to the origin. Well, you gotta learn to love them. You gotta get over your hate for them. Okay? Because this negative 1, right, it would be like negative 1 over 1, and then you'd multiply straight across, right? It's not a negative on the numerator and denominator. All right, so let's talk about number 12 then. On 12, I need f of negative x. That's equal to the absolute value of negative x plus 1. So if I factor out a negative 1 inside of here, and I get x minus 1, then I can take the absolute value of that negative, but that still leaves me with the absolute value of x minus 1. And that's, no matter what I do with that, it's not going to work, and so it's neither. Okay. You didn't have to do this part. I mean, as long as you just know that you can't just take the absolute value of the first one. No, you can't separate them when it's a plus or minus in there. If it's multiplication, that's different. How's it neither? Because these don't match. And you can't just take the absolute value of one of the two things inside of there. Right? If this was negative x minus 1, that'd be different. Well, yes, but let's say that we substitute in a 4, right? So I'm going to say x equals 4. So if I substitute that in, it's going to be negative 4 plus 1, which is going to give me the absolute value of negative 3, right? If you want to take the absolute value of that and tell me this is the same thing, that's going to give me 5. You see I don't get the same thing? So you're not allowed to do that. Anything else?